Hi, and welcome to Lecture 2 for Week 5 of the Quantum Universe for Educators. Before we delve into Heisenberg's great advance in quantum theory, we need to talk a little bit about a couple of pieces of mathematics that will be used in the work we're going to have a look at this week. We don't have to go into too much detail about these pieces of mathematics, but you have to recognize them when they come up and recognize what they mean in essence. So the two things we're going to look at briefly are the Hamiltonian formulation of classical mechanics and the mathematical objects known as matrices. So let's start with Hamiltonian mechanics. This was a formulation that the Irish mathematician and astronomer William Rowan Hamilton came up with. It isn't anything different to Newtonian mechanics. It is Newtonian mechanics, it's just written in a different way, and one that can be generalized in a way that is very easy to more complicated systems than you generally apply Newton's laws to. Hamilton's formulation is a very powerful way of rewriting Newton's laws in a way that can be used to treat complicated systems more simply. And we're not going to get into how that works, but I will show you what Hamilton's equations look like, and I'll show you that if you apply them to a single particle, you just get Newton's second law of motion back out of them. Now, firstly, a word on notation, which you will see used quite a bit. In mechanics, you typically want to describe two things about a particle: its position and its velocity, or equivalently its position and its momentum, which is just equal to mass times velocity. The position is represented as the set of coordinates for the particle in some coordinate system, and the momentum is just mass times the derivative of those coordinates with respect to time. Now, often we want to talk very generally about equations. We don't want to commit ourselves to using Cartesian coordinates or polar coordinates or anything like this. So typically what we do is we just use the letter Q to stand for coordinates. And Q can mean X, Y, or Z. It could mean all three if we want it to. It could be a vector, for example. But we use Q to be general, and then when we apply our equations to a specific problem, then we have to choose what coordinates to use, and we can be more specific then. The momentum of the particle is going to be called P, and in general, Q and P are both functions of time. The particle is, in general, moving. P is just mass times velocity, which is mass times the derivative of the coordinates Q with respect to time t. And we can define the kinetic energy with the familiar formula half mv squared. We generally call kinetic energy T, capital T. A half mv squared is just a half m dq by dt squared. And we can also rearrange a half mv squared and write v in terms of p. So T is equal to p squared divided by 2m. Now, Hamiltonian mechanics is based on a function called the Hamiltonian, which is nothing other than just the total energy of the system. So the Hamiltonian is called capital H, which depends in general upon the coordinates Q, the momentum P, and the time t, and it's just the kinetic energy T plus the potential energy V of the system. If it's a single particle, it's just the energy of that particle. So that's going to be equal to p squared over 2m, the kinetic energy, plus the potential energy, and that's going to depend on the particular problem we're looking at. If there are no forces acting on the particle, there's no potential energy, and v is equal to 0. If the particle is in a gravitational field, then v is just the gravitational potential energy of the particle. If you define the Hamiltonian as the total energy, then the equations of motion of the system, which is the equivalent of Newton's laws, are just encapsulated in these two equations here, which are known as Hamilton's equations. They just say that the derivative of the coordinates with respect to time, which is just the velocity remember, is equal to the derivative of the Hamiltonian with respect to the momentum p. And the derivative of the momentum with respect to time is equal to minus the derivative of the Hamiltonian with respect to q. Okay, and that's all there is to it. To solve any problem in classical mechanics, essentially all you do is write down what the total energy is, plug it into these equations and solve them. And that gives you the position q as a function of time and the momentum as a function of time. And now you know everything you need to know about the system. Let's just prove that it gives us Newton's second law when we want it to. Suppose, for example, we're dealing with a single particle traveling under a gravitational force. So this could be a tennis ball that I've just thrown in the air. The gravitational potential energy I'm going to call V of Q. So let's start with the second of Hamilton's equations. The derivative of momentum with respect to time is equal to minus the derivative of the Hamiltonian with respect to the coordinate Q. Well, the momentum is just equal to mass times velocity, which is mass times dq by dt. So if I differentiate this with respect to time, dp by dt is equal to mass times the second derivative of position with respect to time. That's just the acceleration. So dp by dt is equal to mass times acceleration. So that goes on the left-hand side there. Now, on the right-hand side, minus dh by dq is just equal to minus dv by dq, because only the potential energy depends on the position q in this case. The kinetic energy, remember, depends only on momentum. Now, the definition of force in classical mechanics is that it is just minus the derivative of the potential energy with respect to position. You can show explicitly that this is the case using, for example, Newton's law of gravity. So this is, by definition, equal to the force. So if we plug F into the right-hand side of this equation and ma into the left side, we get fairly trivially F equals ma, Newton's second law of motion. So Hamilton's equations are just another way of writing Newton's laws of motion. But these two laws here, you'll see, are the version of classical mechanics that will be used in Heisenberg, Born, and Jordan's papers that you will read this week. Okay, the second thing we need to establish, or at least mention, is that matrices don't commute. This will be a very important point that we need to understand this week. So I'm just going to refresh you on what that means, and if you need to brush up a little bit on matrix algebra, matrix multiplication, there are some links in this week's material that you can use to do that. So what does commute mean? Well, let's think about just ordinary numbers, like the number 3 and the number 8. Ordinary numbers, when you multiply two of them together, it doesn't matter what order you multiply them in. In other words, 3 times 8 is the same thing as 8 times 3. They're both equal to 24. So 3 times 8 minus 8 times 3 is equal to 0. This is the law of commutation. More generally, if a and b are ordinary numbers, then a times b is equal to b times a, or a times b minus b times a is equal to 0. Okay, now let's take a look at matrices. Now matrices are just arrays of numbers. All right, for example, here are two arbitrary matrices I've just invented, A and B, which consist of 2 rows of 2 numbers each. Now, one of the notable things about matrix algebra is that matrices do not commute like ordinary numbers do. And we can test it for the 2 matrices I've written down here. If we multiply A and B together in this order, then we get this matrix here. First row is 5, 8, second row is 10, 9. You can check this works out yourselves. B times A, however, gives you a different matrix. The first row is 9, 8, the second row is 10, 5. So when you subtract B times A from A times B, you get a matrix that is not equal to 0. Matrices are said to not commute.